Hi, my name is Miguel Hernandez and I'm going to present the article Preparation of Nanostructured Gadolinium Zirconium Oxide Lanthanum Phosphate Thermal Barrier Coatings Under Calcium Magnesium Alumina Silicate Resistance. For instance, the article presents us the introduction where it establishes different aspects and definitions that I consider are going to be pretty important through the whole article, so you can understand the principles that are going to be useful among the whole article. So the first definition that we found is the thermal barrier coatings, that could be defined as the first line of defense in the hot section of metallic components of gas-driven engines. And here we have a schematical representation of a gas-driven engine, and as we can see, it is divided on two different sections that are the cool section and the hot section. And it is important to mention that there are different types of gas-driven engines, and there are those who are focused on the electricity generation applications, and there are the other ones which are used on the aeronautical applications. And in this case, the article is more focused, or it is focused on the aeronautical ones. So here we have another diagram where we can observe better how are the thermal barrier coatings related to the gas-driven engines. And first we can see the metal of the substrate, that is the shell of the turbine, and it is mainly composed about the stainless steel, but there are another alloys that could be useful for these materials. Then we have the thermal barrier coating, and finally the hot section of the turbine. And here we can see that the principal use or application of the thermal barrier coating is to protect the metal or the substrate from the attack of the hot section or the high temperatures that the hot section could reach. Well, the principal properties of the thermal barrier coatings are low thermal conductivity, high temperature capability, and these property could be defined as the capacity of an alloy to support the highest temperature at 1000 hours under 137 megapascals without cracking. So I consider these properties related to another one that is defined as high creep resistance, and the other property is high compliance. Well, the mainly or widely common used material of these thermal barrier coatings is the yttrium stabilized zirconia, and the main production techniques are the electron beam physical vapor deposition, the plasma spray physical vapor deposition, and the air plasma spraying. And this last one, production technique, is the one that is going to be used on this article in order to produce the thermal barrier coating. So then the main problem of these yttrium stabilized zirconium coatings is that when they are operating at higher temperatures, they become more susceptible to environmental damage of materials or particles that are composed of fly ash, sand, volcanic ash, and runway debris. And what occurs with these materials that cause the damage of these thermal barrier coatings? Well, where here we can see an animation of how these these particles or the materials enter to the cabin of the turbine or to the chamber of the turbine, and then when they arrive to the hot section, they get melt. It is around 1200 Celsius degrees when they get melt. And these type of materials or particles are commonly referred as calcium, magnesium, alumina silicate, or more commonly named as CMAS. So the main properties of these CMAS is that they have high degree of moldability and low viscosity, and these properties causes on the thermal barrier coatings a high index of penetration among the cracks and pores of TVCs. So that means if our material, our yttrium stabilized zirconia, has many cracks and has many pores, it is going to be more susceptible to the propagation to the entrance of these CMAS materials. So When they get melted, the CMAS, the interface valley zirconia gets dissolved, and when it gets dissolved, it separates on two phases, the yttria phase and the zirconia phase. And then when this occurs, the initiation and propagation of cracks takes place, and this is mainly due to the volume change of the zirconia phase, which change from monoclinic to tetragonal or vice versa when cooling or heating. And it has been demonstrated that the poor resistance of this yttria zirconia is mainly because when you increase the levels of yttria, the resistance get improves, and it is mainly due to the fact that a formation of an apatite phase takes place, but we are going to talk later about this apatite phase. So there has been some improvements among these thermal barrier coatings, and they consist about the use of the wetting or a sacrificial layer that covers the thermal barrier coating, but at the long lasting term this is not a good solution. So that is why the gadolinium zirconium oxide, among other TVCs, has attracted great attention due to their physical properties and its great resistance to CMAS, primarily because when it dissolves, it also forms the apatite phase and the fluoride phase. And when these two phases are combined, the fluoride one and the silicate one form a protective layer that arrests the further attack of the CMAS. But what happens, unfortunately, is that the cyclic thermal life of this gadolinium zirconium oxide is really poor, and this is mainly due to the bad toughness. So when a material has bad toughness, you cannot observe plastic deformation. So when a crack propagate or initiate, it will crack, and you are not going to be able to observe or to predict, or it is harder to predict when this crack is going to occur, compared to the materials that are with higher toughness. You can observe plastic deformation, and you can predict easier when a crack is going to take place. But the lanthanum phosphate can serve as a toughening agent when it is at around 30 mole percentage. And an interesting fact about the small percentage is when you are going to prepare 1 kilogram of gadolinium zirconium oxide, you will need 167 grams of lanthanum phosphate. So the nanostructured TVCs produced by APS had great importance due to their superior performance when they are operating. And when we are referring to a nanostructured TVCs, it means a coating with nanozones embedded on the coating's microstructure. And here we can see an image of how these spherical particles are separated, and there are some nanozones that are embedded on this microstructure, and these nanozones impart to the coatings, or the properties that they impart are excellent crack propagation resistance and finally corrosion resistance. So now we're going to examine the experimental procedure. And first of all, here is the production flowchart for the coating. So first, the gadolinium zirconium oxide and the lanthanum phosphate were prepared with a process known as chemical co-precipitation and calcination. Then they were mixed on a bowl milling for 8 hours at a speed of 400 revolutions per minute. Then they were dried at 120 Celsius degrees for 8 hours. Then they were calcinated at 1000 degrees for 5 hours, and this was mainly for obtaining a crystal structure or a crystalline structure. And finally, the coating was mechanically removed, so experiments could be conducted in a better way. And then we have the production flowchart of the CMAS, and the powders with this composition that we can observe are the average of the composition of the deposition beam blades in aircraft engines in China. So as we can see, it is a very important average composition. Then the CMAS were suspended in the ionized water Then they were mixed via planetary pulp milling for 5 hours and 400 revolutions per minute. Then they were also dried at 120 Celsius degrees for 6 hours. Finally, the obtained CMAS powders were dispersed in absolute alcohol and fully stirred to produce homogeneous suspension. Then the obtaining CMAS powders were dispersed in absolute alcohol in order to produce an homogeneous suspension, and then they were poured over the surface of the thermal barrier coating, and when the alcohol gets dried, they obtain a completely homogenized surface over the whole thermal barrier coating. So they were obtaining 3 samples of this type, and samples were heat treated in a box electric furnace at 1250 Celsius degrees for 1 hour, 4 hours, and 8 hours. So the principal equipments used in this article were the X-ray diffraction, the Raman spectra, the scanning electron microscope, and finally the transmission electron microscopy. The results and discussions. First of all, the analysis of X-ray diffraction and the Raman spectra were determined in order to identify the phases formed during heating with the melted CMAS. So the phases basically consist on an apatite, anode, and spinel. And the apatite phase is a general reaction product when CMA acts at TVCs containing high content of rare earth, as it is our case with high content of gadolinium. So here we can see the Raman spectra and then the X-ray diffraction pattern. So the first analysis conducted was on the sample of the 1 hour corrosion test, and the main points of this test was that the coating keeps its structural integrity. And one important fact about this is that when they were examining the reaction layer at a higher magnification, it was possible to observe that the layer was composed about two sublayers. It was the upper layer and the lower layer. In the 4-hour sample test, the coating still keeps its structural integrity and has no obvious crack. Another important point was that the nanozones embedded in the coating has some CMA trace, and similar to the 1-hour test, this reaction layer of the 4 hours test could be divided into 2 sublayers. And finally, we have the 8-hour corrosion test, and it is important to say that there was little residual CMAS deposits on the coating surface, and the reaction layer has increased its thickness. Finally, it is also important to say that from these 2 sublayers, the upper sublayer was examined at higher magnification, and it could be found that the apatite type phase experiences a growth stage during prolonged heat treatment. So this means that when you increase the temperature time, the thickness of the upper sublayer increases. And here are some final observations, and that reveal that when taking a closer observation on the CMAS infiltrated nanozones, it could be found that the nanoparticles are surrounded by CMA glass, and the rationale behind these surrounding particles is that the nanozones or the lanthanum phosphate materials have more porosity and a smaller particle size, which causes they could gather more CMAS. But this is not something bad. We're going to see the other final observations. So when the heat treatment duration is extended, the reaction layer grows, forming an upper sublayer, and the reaction layer is impervious, so that means that no penetration of the CMAS could further happen for the molten CMAS, which could prevent further infiltration of them. So this means that the surrounding and beautified particles of the lanthanum phosphate creates even more resistance to the penetration of the CMAS. So the final conclusions are the following. The gadolinium zirconium oxide lanthanum phosphate as a thermal barrier coating reveals excellent CMAS resistant characteristics and 1250 Celsius degrees, and after 1 hour of corrosion duration, a crystalline reaction layer forms on the coating surface, which could be divided into two sublayers. With the increase of the corrosion duration, the thickness of the sublayer has little variation. So this means that the lower layer has a minimum of variation of thickness, but the upper sublayer becomes thicker. And finally, the nanozones embedded in the coating microstructure has significant effects on gathering the molten CMAs, contributing to an even enhanced CMAs resistance of the coatings. Okay, so that is everything from my part. I appreciate your attention and thank you very much.